We're at synthetic division and the remainder theorem to find P of R, 11.2a. If you haven't seen the two previous videos for chapter 11, you can just click on this description and there's links there for you. So I'm going to show you a concept first. We're going to let P of x equal x to the fifth minus 64. I'm going to find P of 2. So that means P of 2 equals 2 to the fifth power minus 64. So we need to do 2 to the fifth power. That's going to give us a 32. Minus 64 is going to give us a negative 32. Now, when P of x is divided by x minus 2, what's our remainder? So we're going to use synthetic division. We're going to set this as a 1, because there's an invisible 1 in front of here, isn't there? And we don't have any values for x to the fourth, x to the third, x to the second, or x. So we're going to put zeros as placeholders. Then we've got our constant minus 64. We're going to divide it by this 2, because we don't have any variables in synthetic division, do we? So we've got a 1, a 0, a 0, a 0, a 0, and a minus 64, a negative 64. We multiply 2 times 1, which is 2. We write it here. We add these. Don't forget to drop that 1 down. So now we've got a 2. Now we do 2 times this 2, and it's a 4, so we write the 4 here. We add them, and we get a 4. We do 2 times this 4, and we get an 8. We write it here, and we add them together and get an 8. We do 2 times this 8, which is a 16. We put it here. We add them, and we get a 16. Now we do 2 times the 16. We get 32. We put it here, and when we add them together, we get a negative 32, just like we did here. Look at that. See that? It both came out as negative 32. All right, now watch what happens here. We're going to let this P of x equal x to the fifth minus 64, just like we did over here, okay? But now we're going to find P of negative 2, the inverse of 2. So everywhere there's an x, we're going to put a negative 2. So that means we've got negative 2 to the fifth power minus 64. That's going to give us a negative 32 minus 64, which is going to give us a negative 96. When P of x is divided by x plus 2. Now remember, over here it was x minus 2. Now we're going to do x plus 2. What's our remainder? I'm going to set all the values that we don't have as a 0 as placeholders. So we've got the 1x to the fifth plus 0x to the fourth plus 0x to the third, and so on. And we've got our constant, that negative 64, that minus 64. Now, because this says x plus 2, and we need it to be in the form of a minus 2, we'll use x minus a negative 2 to divide synthetically. So now we've got a negative 2 here. Now, negative 2 times 1 is a negative 2. We write it here and we add them and we get a negative 2. Don't forget we drop the 1 down. Now we do negative 2 times negative 2, which is a positive 4. We add them and get a positive 4. We do negative 2 times that positive 4 and get a negative 8. We add them together and get a negative 8. We do negative 2 times that negative 8 and get a positive 16. Add them, get a 16. Negative 2 times the positive 16 is a negative 32. When we add them together, we get a negative 96. Just like we did up here. Isn't that something? See how that happened? So the function value, P of R, is the remainder. See, it's the remainder. When P of x is divided by x minus R. Okay, so that's what we're going to be talking about. So here's our remainder theorem. For a polynomial P of x, the function value P of R is the remainder when P of x is divided by x minus R. We can use synthetic division to find function values for polynomials. Let's take a look at this one. I'm going to let P of x equal this 2x to the fifth minus 3x to the fourth plus x to the third minus 2x squared plus x minus 8. So we've got all our exponent values, don't we? So we don't need any zeros. I'm going to find P of 10. So we're going to multiply, and what we're going to do is we're going to multiply 10 times 2, which is a 20. We write it here and add it together. Got our 2 written here. That's a 17. Then we're going to do 10 times 17, which is 170. We're going to add it with the 1, and we get 171. Now we're going to do 10 times the 171 and get 1,710. We're going to add it with the negative 2 and get 1,708. We're going to multiply 10 times this and get 17,080. Add it to the 1. We have 17,081. We multiply 10 times this and get 170,810. We add it with the negative 8 and we get 170,802. So P of 10 equals 170,802. See? Let's try that again. So now we've got a different expression here, but we're still going to find P of 10. And if you look at the exponents, there's no x to the first, is there? There's no x. So we're going to use a 0 to hold its place. All right? That's really important that you do that when you do synthetic division. So we're going to do 10 times 1, which is 10. We're going to write it here and add it to the negative 2. We've got our 1 drop down. That's an 8. Now we're going to do 10 times this 8 and get an 80. Add these two together and get a 73. We're going to do 10 times the 73 and get 730. Add them together, get 731. 10 times 731, we're going to get 7,310, 7,310. Added to the 0, it stays the same. 10 times this 7,310, it's going to give us 73,100. We add it to the 20, we get 73,120, and that's our P of 10. That's what it equals. All right? Synthetic division. Now, here's proof of the remainder theorem. In the equation, P of x equals D of x, that's the divisor, times Q of x, that's the quotient, plus R of x, that's the remainder, is the basis of this proof. Now, we talked about this in the previous videos. This is like saying 12 is equal to 2 times 6 plus 0, right? So if we had division and had 12 divided by 2, that would be the divisor. If the quotient would be 6, we'd have a remainder of 0. So that's the basis of this proof. If we divide P of x by x minus r, we're going to get a quotient Q of x and a remainder r of x, and it'll be related like this. We'll have P of x equal x minus r times the Q of x plus r of x. All right? And that remainder r of x, it must either be a 0 or have degrees less than the degree of x minus r. Okay? So it's either got to be a 0 or have degrees that are less than the x minus r. So r of x must have a degree of 0. That means it must be a constant. So let's call this constant r, and we've got P of x equals x minus r times the Q of x plus the r of x, right? That's our expression here, all right? This will be true whenever we replace x by any number. We could put a 2 there, we could put a 99 there, doesn't matter. Whenever we replace x by any number, it's going to make this expression true. And if we replace this x with r, then we'll have P of r equals r minus r times Q of r plus r, capital R. See that? It's going to make a 0, isn't it? And when we multiply a 0 times the Q of r, we're going to get a 0 again. So now we just have an r, don't we? That tells us the function value P of r is the remainder when we divide P of x by x minus r. See? That's the proof of the remainder theorem. Let me step back a little bit here so you can see that. All right. Now our next video is going to be 11.2b. We're going to talk about given numbers as a root of P of x. There's going to be a link to those 2 previous videos for Chapter 11, and there's also going to be a link to video 6.5 back from Chapter 6 where we learned about synthetic division. There's a step-by-step instructions, and it also shows it in the 2 previous videos. All right, just click on this description and there'll be links to those. All right, so that is synthetic division and the remainder theorem to find P of r, and I hope you're doing okay. And I always worry that, did I explain this well enough? Do you understand? Because I know some of this can become very difficult. But good luck. I believe in you. All right? I'll see you next video. Bye.